Right. So, in this lecture we will continue with our analysis of the Bayes networks. So, recall that in the last lecture we considered belief networks which are in the form of a polytree, which means that between any pair of nodes in the belief network we have exactly one undirected path. Okay. Coming back to the definitions, our objective is to compute the generic query P of x given E, where E is a set of evidence, which means that it is the values of a set of variables in the belief network, and our objective is to compute P x given E. So, the evidence nodes can be above x in the belief network and can be also below x in the belief network. So, we partition E into two parts, namely E x plus and E x minus. E x plus consists of those evidence nodes which are predecessors of x, and E x minus consists of those evidence nodes which are descendants of x. So, they may not be immediate parents or children, but they are ancestors or descendants. Then we had the following definitions, namely that for the node x, u1 through um are the parents, y1 through yn are the children, x is of course the query node, and E is the set of evidence variables, and we want to compute P x given E. So, we had initially formulated this as follows, that P x given E is P x given E x minus and E x plus. So, E is just partitioned into the two sets E x minus and E x plus, and then we rewrite this using Bayes rule as P of E x minus given x E x plus and P of x given E x plus. So, this was written in this way, so that we always have the effects on the left hand side and the causes on the right hand side, right. So, we write it in the form in which the Bayes network itself is given, and then we showed that since this is a constant, so we can replace it by alpha, and the first term reduces to P E x minus given x, because the node x separates E x minus from E x plus, and then again we have P x given E x plus. We analyzed the first term in the last lecture, and then showed that the first term can be represented as sigma over all the parents of x, and P of x given u, and then the product of all these independent terms, namely probability of each ui given the evidence connected to the ui except through x. So, we had seen that these entries can be found out from the conditional probability table for x, and these terms can be recursively computed, because they are again the parents of x, and because we are going from x to its parents and from its parents to its parents and so on. So, this term will recursively take us right up to the first level nodes, and in the first level nodes they will become independent of the evidence, and so they will have the values from their probability tables directly, right. So, this part is solved now. Now, what we need to do is still to show that how do we compute probability of x, probability of E x minus given x, right. So, this first term out here is something which we have not yet addressed. So, today we will first look at the computation of P of E x minus given x. Now, coming to the picture that we had, text please, text please. Okay, let us continue with this. So, we have, yes, uh, for each yi we have a parent, one or more parents, which we will call say for y1 we will call it z1 1 to z1 j through z1 k, right. Then for yn it will be zn1, zn2, zn3 and so on, right. So, what we are going to do is when we, so this is the set of evidence nodes in this part is what we are calling as Ex minus, right. Now, what we are interested right now is in computing probability of Ex minus given x. So, we will try to decompose this term in terms of the probabilities of these children given the evidence in their predecessors, right. So, that is why we are interested in just considering the immediate parents of these yi nodes, right. Y1 through yn are the children of x and we are looking just at the immediate parents of these, right. So, the evidence in each yi box is conditionally independent of the others given x. So, if x is given, then the probability of y1 is independent of the probability of y2 and the independent of probability of yn, because this node x will deseparate them provided provided that x is given, right. So, we can rewrite p Ex minus given x as the probability over Eyi except x given x and take their product. Now, is that understood? No. Okay. What we are trying to compute here is that the probability of the set of evidence nodes that are below x given x, right. So, each of these Ex minus consists of what? It consists of text please. It consists of some of the evidence nodes around y1, some evidence nodes around y2, some evidence nodes around y3 and so on, right. Now, our claim is that if x is given, then the set of evidence nodes around y1, their probability is independent of the set of evidence nodes around y2 and their probability is independent of the set of evidence nodes around y3 and so on. Okay. So, therefore, Ex minus can be partitioned into the set of evidence nodes around y1, around the evidence nodes around y2 and so on, right. So, we partition the evidence Ex minus like that, and that gives us each of these Eyi except x. Recall that the definition of Eyi except x is the set of evidence nodes connected to yi except through x, right. So, after partitioning that out, because these evidence nodes are independent, so we can split them up into a product of their probabilities. Okay. Right. Then we average over yi and zi. Now, let us understand what is this averaging. Now, when we look at the probability, text please, when we look at the probability of a particular event here, we can average out over its parents. Remember that the probability of yi, we can write that as probability of y1 and z1 1 plus probability of y1 and if you look at the parents, let me suppose we have a node y and we look at its parents, say z1 through zk. So, we can split up y as this probability of y times say z1 zk plus z1 dash zk, and all 2 to the power of k combinations like this, right, and we can distribute it out, average it out over that. Is that okay? Yes or no? Yes, like probability of alarm, you can write this as probability of alarm, burglary, earthquake, probability of alarm, burglary, not earthquake, probability of alarm, not burglary, earthquake, and probability of alarm, not burglary, not earthquake. Yes, average it out. Because we are talking about probabilities, so averaging means taking up the sum over taking the weighted sum actually, right. So, if we do that for this term P E y I except x over x, then what we have is, if we take it over y I and z I, then we have this x I, y I, z I here, right, and summation over all y I and all z I, and we also have the term P y I z I given x. Just have a look at this. Not clear?
What is summation over all y?
See, recall our burglary alarm example. So, we had alarm and we had burglary and we had earthquake, right. So, this was what we had. So, if you look at probability of alarm, then we can write this as probability of alarm, right, given burglary, earthquake times probability of burglary and earthquake plus probability of alarm given not burglary, earthquake times probability of not burglary, earthquake plus, got it? So, this is what we are doing here. So, if you look at this term now you see it is exactly the same thing that is happening. We have all these burglary, earthquake kind of pairs here, and then we have the probability of these burglary, earthquakes, etc. And because this was the conditional probability with x, so we have the conditional x here as well, right. Is it clear? It is the same thing that we are doing here. We are just averaging out over the parents of y I, right, over the y I and the z I. See, you can do this, see, regardless of what y I and z I are, you can always do this averaging. You take any two variables and you can always write this average and it is a correct probability expression, isn't it?
Summing over y I.
Okay, why I am doing that will become clear later on. But the question is that if you just have any two variables, additional variables, two or more variables, can you or can you not do an averaging out like this, right. So, the question is that if I have any variable, say p of x given y, and I have variables say z and v, then can I write this as probability of x given y z v, right, times probability of ZV given Y plus probability of X given Y Z dash V times probability of Z dash V given Y, and so on. The question is, can I write this regardless of what Z and V are? I can. Okay. I can do that. So, that is what we are saying, that for the time being what we are doing is we are averaging out over yi and zi. Why we are doing that? That will become clear as the analysis progresses. But the fact is that we can always do this, there is no, it is not incorrect to do this, right. Now, whether it is useful or not, that we are going to see. Okay. Now, averaging this out, then we do the following thing. We break this EYI except x into two independent components, EYI minus and EYI except x plus. Now, let us see what is meant by this. So, if we go back to our picture here of the Bayes network, so then we have this yi, right. So, we have some evidence above the yi and some evidence below the yi, right. So, the evidence above the yi will be called EYI except x plus. So, all the evidence which is connected above yi except those which go through x. So, we are not considering these ones. That will be called EYI except x plus, right. And whatever we have below the yi is simply E of yi minus. Here we need not consider, we do not have to specify except x, because whatever is below yi does not have anything to do with x at all, right. Clear? Okay. So, having broken up this EYI except x into those two parts. So, we have this split up as EYI minus given x yi z I, right, and PEYI except x plus this thing. Now, we are saying that these two this probability term can be split up as the product of these two terms, because these two are independent. And why are they independent? Because we have yi here. So, yi is given. So, if yi is given, then yi deseparates, it separates out the EYI minus and the EYI plus, right. So, therefore, these two are independent and we can write them as a product of two probability terms. So, this is where we are right now, that we have these two probability terms. EYI minus here is independent of x and zi given yi. Right? Because yi separates them. If you look at the picture, see EYI minus is all the evidence that is here. So, that is independent of x and zi, because it has to go through yi and yi is given, right. So, therefore, we can simplify this term, the first term, as PEYI minus given yi. The second term, in the second term, EYI except x plus is independent of x and yi, because why is it independent? Because again yi separates it, right. So, therefore, we can simply write this as PEYI except x given zi, right, and then we have this term which we originally had, right. See, what we are trying to do is, if you look at the picture, what we are trying to do is, we are trying to split up the probability terms in terms of the parents of yi and the children of yi. So, that recursively from the term for x, we will be able to recursively bring it down to the terms of its children, right. That is the idea that we are trying to do. Then we apply Bayes rule to the term p yi except x plus, and that gives us this term, that p zi except yi this thing, and p EYI except x plus divided by PZI. Right. So, this simply it is this term which gets replaced by this term using Bayes rule, right. The reason we are doing this is that this is again in the wrong direction. This is in the wrong direction. This is the cause and this is the effect. So, we need to turn it around. Whenever we need to turn it around, we use Bayes rule, right. So, after using Bayes rule, here you can see that we have it in the right order. So, Zi given p yi except x plus, right. Okay. Then after rewriting the conjunction of yi and zi, we get this. See this p yi zi given x has been broken up into p yi given x z and p zi given x, right. Again standard way of writing this using Bayes rule, right. Okay. After having done this, then we note that p zi given x is equal to p zi because z and x are deseparated. If you look at the figure again, this and this are deseparated by this, right. So, if there is no evidence about this, then this and this are independent, right. And in this particular probability term, we are looking at p zi given x. So, yi is not given. So, therefore, zi and x are independent. So, therefore, we can write p zi given x as simply p zi, and also p yi except x plus is a constant, because this has not this does not have any x y etc. So, that gives us this term where we replace this constant term by beta I, right, and we also replace p zi given x by p zi. Okay. Then what do we have? So, then this is the reduced expression that we have. Now, the parents of yi, namely the zij, are independent of each other, right, and why are they independent of each other? Because yi is not given. In this term, because yi is not given, so these zi are all independent of each other. So, therefore, and we combine all the beta i's into one single beta, that gives us finally this expression. Okay. Now, if we look at each of the individual terms, then this is a recursive instance of p e x minus given x, because it talks about p y I minus given y I, but it is a recursively smaller instance because we have moved one level down. From x we have moved into y I, which is a child of x. Right. Then p y I given x and z I is a conditional probability table entry for y I. So, we get that directly. Right. And p of z I j given E of z I j except yi is again a recursive sub instance of the p x given E calculation. But because we have this except yi, so therefore, the evidence set has reduced. See, in order to guarantee termination, we have to show that the recursive sub instances that you create are smaller than the original one. So, how is this smaller than the p x given E calculation? It is smaller because the set of evidence nodes is now reduced, because the evidence nodes which are through yi are not there anymore in this computation, right. So, then again recursively we have to apply the same procedure. Okay. So, what was the objective of going through all these computations? The objective of going through all these computations was to show that if you use Bayesian analysis, then things can become pretty complex if you have Bayes networks which are not small enough, right. Otherwise, if you have to find out the probability of any particular kind of event or any conditional event, then it can become really complex to compute this, right. Moreover, what we have seen so far is only tree like instances. We have looked at only tree like instances, but in general the Bayes network need not be tree like, it can be a complete graph also. If it is a graph, then we can have further combinatorial blow up. Okay. So, what we are now going to see in the remainder of this chapter is what alternative does one have to Bayesian reasoning, right. Probabilistic reasoning is very important, because as we had discussed at the beginning of the lecture of this chapter, that there are cases where you do not know of the exact cause effect relationships, but we derive that statistically. So, therefore, it is easier to think in probability terms than to be able to comprehensively define all kinds of causes for a given effect, right. So, that is why people do use probabilistic reasoning, and the problem that we see here is if you use strict Bayesian reasoning, then it can become pretty complex. So, people have thought of other ways of doing this which require less computational overhead. So, we will look at some of the other theories in brief and see how our computation goes there. But before we move into that, I would just like to touch upon what happens if we have Bayes networks which are not tree like. So, what approaches can we have there? So, they are called multiply connected belief networks. Belief networks which are not singly connected. Singly connected is the ones that we were talking about. Between a pair of nodes, we have only one undirected path. What could be an example of a multiply connected belief network? Okay, let us look at an example which is as follows, that we have the event cloudy. And then we have a sprinkler and we have rain and we have wet grass, and the sprinkler should normally not go off when it is cloudy, because it expects rain. If it is cloudy, then we can have rain, and both of these has as effect weight grass, right. So, this is an example of a network where we have multiple connections. Wet grass can be result of sprinkler, it can also be the result of rain, and both are conditionally dependent on whether it is cloudy or not, right. Now, how do we analyze this kind of networks? Right. The problem in our previous approach will be that you can have, if it is a multiply connected network like this, see what was happening there was we were recursively decomposing the problem into smaller and smaller problem instances, and as we were going out from the center of the tree towards the leaves, our problem size was diminishing, right, and when we reach the leaf nodes we are solved. But here what may happen is that different paths in the network can create similar sub problems along different paths. So, it is not just that you are propagating from the center outwards, you are, but what may happen is through some path you generate a sub problem instance, through another path also you generate another sub problem instance, and depending on the number of paths that you have in the network, the number of sub problem instances can be growing, right. So, again it boils down to things like dynamic programming and what ways to compute those. For example, if you have similar sub problem instances, it might make sense to not compute them in a depth first manner, or if we do compute it in a depth first manner, then to memoize it in some way, right. So, people have also thought of alternative approaches for handling multiply connected belief networks, and we are going to look at a couple of these approaches. Firstly, let me add on some probability values here. Just a minute. So, let us add some probability values here. So, in this table we will have cloudy versus probability of sprinkler, right. So, in this table, let us say for true we have 0.1, for false we have 0.5. So, if it is not cloudy, then the probability of the sprinkler going off is 50%, and otherwise it is just 0.1, right. And let us say probability of cloudy is simply 0.5, and then here we have cloudy and probability of rain, and let us say that if it is true, then the probability of rain is 0.8, if it is false, then the probability of rain is 0.2, right. And then for this one we have sprinkler, rain, and probability of wet grass. So, we will have 4 possibilities here, namely true, true, and then we have a probability of 0.99 that the grass is wet, then true, false, probability of 0.9, false, true, probability of 0.9, and false, false, then we have a probability of nearly 0, 0. So, which means that it is almost 0. Now, what the first method attempts to do, or the clustering kind of method attempts to do is to combine these two events into one event. So, slides please. Yes. Transform the net into a probabilistically equivalent polytree by merging offending nodes. So, what we are going to do here is we will try to combine these two into one single node, but then the event that we have on the right hand side, the probability of the event, that is not going to be just sprinkler or just rain anymore. It is going to be sprinkler plus rain kind of stuff. So, what will happen is we will reduce this to an equivalent network where we have cloudy, we have sprinkler plus rain, and we have wet grass. The probability of cloudy remains as 0.5. Now, the interesting thing will be the probability table for this one. So, we are going to have C, which is cloudy as before, and we will have this probability of S plus R, which we will call as the new random variable x. So, it is just the sum of these two random variables, right. So, again we can have true true, true false, false true, and false false, and the conditional probability of this thing is going to look like, if it is true, then this is 0.08, then this is 0.02, then this is 0.72, and this is 0.18. Where are we getting these probabilities from? So, if you look at this this thing that we had for the sprinkler 0.1 here and 0.8 here when it was cloudy, right. So, the probability that we have both is 0.08, right. We had when it was cloudy, right. So, this was what we had for true true. Okay. How do we get the true false? 1 this times 1 minus 0.8. Are you getting it? This is the probability of S given C, and this is the probability of R given C. When we are looking at true false, it is probability of S and probability of not R, and probability of not R given C is 0.2. So, 0.2 times 0.1 gives us 0.02, right. So, in this way, again when we look at false true, so this is going to be 0.9 and 0.8. So, that gives us 0.72, right, and false false is 0.9 times 0.2, 0.18, right. So, similarly, we have also the entry for C as false, in which case we will look at these entries in the table, right.
For the sprinkler we have given cloud when false, it is 0.5.
For the sprinkler given
False.
yes. So, this is 0.5, yes.
So, where it is used?
It will be used now. See, when we look at cloudy, not cloudy, then what is the probability that we have the sprinkler and the rain? So, that is going to be 0.5 into 0.2, so 0.1, right. Then when we look at cloudy, but we have sprinkler not rain, so that will be 0.5 into 0.8, right. So, that is going to be 0.4. Then not cloudy, but we have rain, right. So, that is going to be 0.5 into 0.2. So, 0.1, right, and then not cloudy, and we do not have rain and nor do we have the sprinkler. So, that is going to be 0.5 into 0.8, yes. So, 0.4, right. So, that is how we get the conditional probability table for this. What about the conditional probability table for this? For this we will again have S plus R, and we will have PW, and then this is going to be just as before. It is going to be true true, true false, false true, and false false, and we have exactly the probability values that we had previously, namely these values 0.99, 0.9, 0.9, and right. Now, having done this, we have converted the multiply connected belief network into a single connected network, right. Then we use the same algorithm as we have done. Okay. So, that is one approach, right, to handling multiple connected belief network. Another approach is conditioning methods, where we instantiate variables to definite values and then evaluate a polytree for each possible instantiation. Okay. So, then the idea is that we have this multiply connected belief network. What we are going to do is we will instantiate one of these variables to some definite value, right. So, that is going to take off that part, and then we evaluate the remaining network, which is a polytree. But one of the most popular ways of analyzing belief networks is stochastic simulation methods. So, what we do is we use the network to generate a large number of concrete models of the domain that are consistent with the network distribution, and they give an approximation of the exact evaluation. Now, let us understand what happens here. Here we start from the topmost node, from the start node, and we progressively go downwards, right. So, let us see what we are going to do. We will start by choosing the value of cloudy with a probability of 0.5. Right. Now, what do we require in order to do this? We require to be able to simulate a distribution which gives us samples of the value of cloudy with 0.5 probability. So, suppose we have a generator which generates the value of cloudy, and we want that generator to be such that half of the times it gives yes, half of the times it gives no, right. So, that is what we mean by simulating the probability distribution. So, we pick up the value of cloudy by this random choice, right. Having picked up the value of cloudy, then suppose cloudy is true. If cloudy is true, then we will pick up the value of sprinkler using a distribution which says yes 10% of the time and no 90% of the time. Understood? Why we are choosing that? Because we know that if cloudy is true, then the probability of sprinkler is 0.1, right. Then similarly, if cloudy is true, then we pick up the value of rain with a probability distribution generator, which will say yes 0.8 number of times and no 0.2 number of times, right. And then having chosen the values of sprinkler and rain, then suppose we have chosen sprinkler to be true and rain to be false, then with 0.9 probability we will choose wet grass to be true. Okay. So, it is all in simulating the probability distribution and generating this, right. Then we will note down that what is the whether we got wet grass or not. Okay. Again repeat this experiment, large number of times, and then find out what is the probability of the event that you wanted to determine. Okay. So, this is going to simulate the scenarios which the belief network captures with the biased by the probability distribution of this belief network, and then eventually after doing a large number of experiments, then you see what is the probability or what is the percentage of times where the event that you whose probability you wanted to compute, how many times did that occur. Suppose we wanted to compute the probability of cloudy given wet grass, right. So, we do this simulation and determine on how many occasions did we have cloudy and wet grass, and on how many occasions did we have cloudy and not wet grass, right. So, we do that, and then from that fraction we conclude the probability value, right. And there has been a large number of different kinds of ways of doing this simulation. Some of the most popular ones are Monte Carlo simulation. You must have heard of Monte Carlo simulation. They actually do this kind of simulation. Then there are more recent methods like Gibbs sampling, right. So, if you can read up the book and some other related references that are given here to know more about the different kinds of stochastic simulation methods. In fact, the simulated annealing method that we had studied is also a kind of stochastic simulation, right. So, in the next class what we will do is we will look at some of the other kinds of reasoning that people do, probabilistic reasoning that people do, like fuzzy logic and other kinds of things, and see what are their relative merits with respect to Bayesian analysis. Okay. Thank you.
(1951). A young nation aspiring to find ways to fulfill a dream lays the foundation of an institution that will give aspiring technocrats the license to fly high. The first Indian Institute of Technology is born at Kharagpur. Founded on the basis of the recommendations of the N.R. Sarkar Committee that was set up in 1945 to consider the development of higher technical institutions in India, the institute was first established in 5 Esplanade East, Kolkata, before it moved to Kharagpur in 1951. With Sir Gyan Chandra Ghosh as the first director and Dr. B.C. Roy as one of its founding guardians, the institute established itself as the symbol of a young, dynamic and resurgent nation. As top students rubbed shoulders with the most celebrated of professors and scholars, visions took shape. And IIT Kharagpur continued to play the pioneering role that was envisaged for it, enabling India to become a knowledge powerhouse that it is today. every stage of its evolution, IIT Kharagpur remained ahead of its times. It provided the best of facilities for the budding technologists, helping them shape their own as well as the nation's future. Indeed, today IIT Kharagpur has blossomed into a time-tested, venerable institute of learning, with the rich experience of converting individuals into brilliant professionals through 50 glorious years. As you cross the campus gate, you feel the distinct nip that is IIT Kharagpur. The spirit of objective inquiry and lateral thinking hangs heavy in the air. The modern township-like campus of IIT Kharagpur, set in sylvan surroundings, is self-sufficient in all respects. From modern banks to the good old post office, from vast playgrounds and well-equipped gyms to modern auditoria and open-air theaters, and from the quiet fiber-optic linked residential quarters for the faculty to the web-enabled hostel rooms for the students. At IIT Kharagpur, lush green bowers of tranquility coexist with smart cards and ATMs. Spread over 690 hectares of sprawling cyber habitat, 120 kilometers from Kolkata, IIT Kharagpur is one of the largest network campuses in Asia. Just the academic complexes itself spreads over a built-up area of about 2 million square feet, of which 150,000 square feet is the new complex that commemorates the Golden Jubilee celebrations. And that's not all. It is the only IIT to have conquered territory beyond its own through cutting-edge courses offered in its extension campuses at Kolkata and Bhubaneswar. IIT Kharagpur is not just about its large campus, but its diverse range of activities. It offers the widest spectrum of disciplines, ranging from aerospace, biotechnology, cryogenics, to architecture, mining and agricultural engineering, supported by strong faculties of sciences, humanities and management. There are more than 30 departments and centers that offer the largest number of undergraduate and postgraduate courses amongst the IITs. The courses are ever evolving and show the way for other sister institutions. The richness in its diverse activities is showcased by the technological support the institution provides in areas like architecture, agriculture, post-harvest technology and medical sciences. The institute has revolutionized and popularized rice milling technology. The other major contributions of IIT Kharagpur have been in the critical fields of defense, railways, space research, power systems and petrochemicals. All these activities directly empower the human requirements of the nation. Advanced facilities at the Institute make it possible to undertake cutting-edge research and service-sponsored research projects. The array of equipment ranges from aerodynamic testing laboratories to intelligent machining centers, atomic spectrometers, to VLSI design labs, molecular beam epitaxy, to anechoic chamber, fast protein liquid chromatographs, to liquid nitrogen plants. The cutting-edge technologies are at par with the best research facilities across the globe. In fact, the volume of research and development activities at the Institute is incredible. In terms of the number of patents it owns, the volume of industrial consultancy it provides, and the revenue that it earns from all these make IIT Kharagpur a class apart and strengthens its position as the true pioneer in technological education in India. The Institute Library deserves a special mention. Fully web-enabled, it is one of the largest in Asia with over 324,000 volumes of material, including books, videos, microfilm, and patent documents. That ensure a student's mind develops at the right pace. Indeed, in this golden jubilee year, as the celebration continues, Pandit Nehru would surely have been a proud man today. For him, IIT Kharagpur was always more than just an institute of technology. In his own immortal words, it is indeed